Now let's look at the first problem in binary searching technique, which is find peak element. So as part of this problem statement, what we have gotten is we have gotten an array of nums, and in that array of nums of I is never equal to nums of I plus 1. That means that two adjacent elements will never be equal. In that array of values, we will have to find the peak element, and we need to return that specific index back to the user. So that is the problem statement that we have gotten. In a minute we will see a couple of examples and you will get a better understanding of this exactly. But right now, a peak element is an element that is greater than its neighbors. That means that, let's just say, if x, y, z are the three numbers and y will be the peak value if y is greater than both x and z, then y is the peak value. That means that it is greater than both its left neighbor and right neighbor. Then only we will call that as peak value. And one more thing is that whatever the array that we have gotten, right, it can have multiple peak values, and in that case we can return any of the index that is up to our choice. Okay, so that is the logic that we have gotten. So here, just look at the example that we have gotten here, right? So it has the values 1, 2, 5, 2. Now looking at this array of values, we can clearly say that 5 is the peak value because 5 is greater than 2 and minus 2. Okay, similarly if you look at this other example, right, it has multiple peaks, like we've gotten in the problem statement, there is a chance that we can have multiple peak values, right? So here the multiple peak values are nothing but 7 and 8. So either we can return the index of 7 or 8. It is completely up to us. So one thing that you need to notice here in the examples that we have gotten is we will see the values raising till a value, and after that again they will drop to a lower value and they again start increasing. And if there is another peak inside the given array of values, after this value immediately they will go down to another lower value and they again start increasing. So ultimately here, whatever the array of values that we have gotten, right, in that there are multiple sorted sections. So that is an important thing that you need to understand. Later on we can use that property for solving the problem effectively. Okay, so that is the problem statement. Now obviously if you look at this problem, right, we can solve this problem in many ways. One of them is using the brute force technique, right? So here array of values that we have gotten is 1, let's just say 7, 0, 3, 5, 8 and 4. So these are the array of values that we have gotten, and the indexes are 0, 1, 2, 3, 4, 5 and 6. Now let's look at what is the brute force way to solve this specific problem. Now obviously what we can do, we can start the iteration from the index 0 and we can always go to the right. So what we can do is, at any point of time, what we will do for I equal to 0 to length of the array that we have gotten, immediately inside what we will do, we will compare if array of I is greater than array of I plus 1, then what is going to happen? This array of I is greater than its next value. That means I plus 1. Let's just say if we are at index 1, right? 1 has value of 7 and index 2 has value of 0. That means that 7 is obviously the peak element. Now we need to return the index, right? So here we can immediately return I itself back to the user. So this is the brute force approach for solving this specific problem. But remember that if we had gotten the values like 1, 2, 3, 4, 5, 6, so we always need to assume the worst case scenario for solving a problem, right? Let's just say the array of values that we have gotten is 1, 2, 3, 4, 5, 6. Now the peak value inside this array is nothing but 6, right? So obviously we will need to return 6, but for that the amount of time that it takes is n, which is nothing but number of elements inside the given array. So we have to find a better way to solve this problem. That is where binary searching technique comes into picture. Why? Because like I mentioned in the problem statement, the values will start from a particular value and they increase till a particular value, and after that again they go down to a lower value and till again another peak, they can start increasing. And if there are again multiple number of peaks, what is going to happen? They will drop down to a lower value and they again start increasing. So these sections of arrays are nothing but sorted arrays, right? So we can use binary searching technique and make few changes to that binary searching technique, and we can find the peak element in the order of log n units of time. Okay, but anyway, this is the brute force approach. Now let's look at how can we apply binary searching technique for this specific problem and find the peak element effectively in the order of log n units of time. So here, since we are going to apply binary searching technique, what we will do, we will use couple of variables start and end. Start will be pointing to the index 0 and end will be pointing to the last index that we have. Immediately, this is our search range, right? 0 index to 6th index, anywhere the value can be present. So here what we will do, we will calculate the middle. Middle is nothing but 0 plus 6 divided by 2, which is nothing but 3. So index 3 is where we have the middle. Now what exactly we will do is, we will compare the value at this middle index plus this middle plus 1th index. Remember, we will compare the value with middle index with middle plus 1th index. So here the value we have at this middle index is smaller than the value we have at the middle plus 1th index. In that case, what exactly we will do is, there is a chance that since the value at middle index is smaller than middle plus 1, that means that the values are increasing after middle index. So that means that the greater value, the peak value, is going to be present on the right part of the search range. So what we exactly do is, we immediately update start to middle plus 1th index. So right now start will be pointing to middle plus 1, which is nothing but 4, and end is there at index 6. Again we will calculate the middle. So now again, if we try to calculate the middle, what is going to happen here? 4 plus 6 divided by 2, which is nothing but 5. So middle is at 5. Now we again compare middle index value with middle plus 1th index value. So here we have 8 and middle plus 1th is 4. That means that the value is decreasing. That means that the peak value is there on the left part of it. That means here what we will do, start is at index 4 and end we will be updating it with the middle index itself. Okay, now start is at 4 and end is at 5. Now again we will calculate the middle, so which is nothing but 5 plus 4 divided by 2, which is nothing but 4.5. we will floor, so index 4. Now what is there? Now the middle that we have gotten is nothing but index 4 itself. Now what we will do, we will compare the middle value with middle plus 1th index value, right? So 5 and 8 we will compare. Obviously 8 is greater, right? So what we will do, start we will update with middle plus 1th. So end is there at index 5 and right now start is also there at index 5. So at this point of time we can stop the logic because start has become less than end. So as long we will run this logic of calculating the middle and everything, as long as start is less than end only. In that case both are at the same position, so we can stop the calculation. And now start is pointing to the index 5. So 5 is nothing but where we have one of the peak value, so we can return index equal to 5. You remember in the problem statement we have gotten that either we can return, it is up to our choice. If there are multiple peak values, we can return either of them. So here either we can return 1 or we can return 5, but we have written 1 here. Okay, very simple implementation. Whenever we try to get the middle, right, based on start plus index, we will compare the middle index value with middle plus 1th index value, and if at all the middle plus 1th index value is greater than the value we have at the middle, we will immediately update the start to middle plus 1 because the values are increasing. That means the peak value is going to be there on the right part. Otherwise, we will simply update the end with middle itself because including that middle, any value can be peak value on the left side. Okay, so that is an important thing that you need to understand here. Okay, now anyway that we have discussed the algorithm, let's quickly write the pseudocode for this. So what exactly we will do, we will write one function called find peak. It will take a array of values. Immediately what we will do, we will define a couple of variables like start pointing to index 0 and end we will initialize it with length of the array -1. Okay, now immediately what we will do, again another helper variable, anyway we are going to calculate the middle, right? So we will initialize middle with -1. Immediately, as long as we will loop through, as long as the start is less than end, what we will do, we will calculate the middle. Middle is nothing but start plus end divided by 2. Once we get this middle, what we will do, we will compare the value of middle with middle plus 1. So at any point of time, the nums array of middle is less than the value we have at the middle plus 1th index. The peak value is on the right side. So what we will do, start equal to middle plus 1. Okay, if this is not the case, then the peak value could be any value including that middle value from start till middle. So immediately we will update the end with the middle index. Okay, once this while loop is done, whatever the start index that it will be pointing to, right, after this loop condition, we can simply return start, indicating that it is the peak values index. So ultimately our aim is to move this start index to the peak elements index. Okay, so that is the small changes. There are few changes in the traditional binary searching technique, right? In the case of traditional binary searching technique, we will be searching for a particular value, and if we found that value, we will immediately return that. If not, either we will restrict the search span to right part of the array or left part of the array. But here, instead of comparing the middle index value with some target value, our aim is to find the peak value. That is the reason why we fine-tuned it to compare middle with middle plus 1, and if we found the value in the end, once the loop is completed, our index will be our start variable will be pointing to the peak element index, and we can return it. Okay, so that is the binary searching technique implementation. Obviously here the amount of time it is going to take will be log n units of time, and the space is nothing but only 3 variables, right? Start, end, and middle, and these 3 variables will going to consume anyway constant amount of memory. As a result, the space complexity will also be constant. Okay, so that is the effective way of finding the peak element inside a given array of values. If at all, if you have any doubt, what you can do is you can try taking a traditional array. Let's just say 1, 2, 3, 4, 5, 6 are the values. So here indexes are 0, 1, 2, 3, 4 and 5. Now immediately start will be pointing to 0, end will be pointing to 5, and the middle is nothing but 5 by 2, which is nothing but 2.5. So the middle is this. Immediately what we will do, 3 and 4 will get compared. So 4 is greater than 3, right? So what will happen? The search range will become this one. Now 3 plus 5, 8 divided by 2 is nothing but 4. So middle is 4. Immediately 5 and 6 get compared. Obviously 6 is greater than 5, right? So immediately both start and end will be pointing to the same index, and at that point of time, start and end are equal, so there is no reason that we need to run this loop. Both are equal, right? So we can stop the execution at that point of time. Start is pointing to index 5, and that 5 is nothing but having the 6, which is nothing but the peak value in this array of values. Okay, so very simple implementation. You just need to fine tune the binary searching technique with this custom logic to have the solution ready in order of log n units of time. Okay, now that we have seen the pseudocode, let's quickly go ahead and write the implementation and validate the same on various scenarios.